Welcome back, everybody. So now we're going to prove transfinite induction. So remember, induction was a principle in the natural numbers that allow you to prove things by showing, if you wanted to show that every natural number had a property, what you did was consider all the sets that have the property, all the elements that have the property, and then prove that this set is inductive. That if an element is inside, then the next one is also inside. So ordinals, well orderings actually, have a principle that is a version of this induction. It's called transfinite induction. In a sense, the ordinals are kind of like, they go beyond the natural number. They go beyond the finite numbers, and that's why they are called transfinite. And the induction for natural numbers is going to be a particular case of this induction. Let's see what it looks like. Before saying the statement, we need this notation. So seg t is going to denote the initial segment of A up to T. So essentially, if we have here, A is a linear ordering, like say here is A is as a linear ordering, and somewhere here is an element T of the linear ordering, then seg T is the segment of everything that is below. This is seg T. All the x's that are below T. Okay, it's called an initial segment because you can also consider the final segments. That's why you clarify that it's initial instead of final. Okay, nothing about this definition. It's just all the elements strictly below T. Here is the transfinite induction principle. So we have to start with the well ordering. It only works for well orderings. And it says the following: if you have a subset of the well ordering which satisfies this property, which is essentially what we used to call B is inductive, and it says that whenever you have an element, like for every T in A, if the initial segment below T is included in B, then T is also included in B. Notice the initial segment below T doesn't include T, right? So T does not belong to the initial segment below T. The property says that if the whole segment is included in B, then so is T. So we only consider B's without properties. And what transfinite induction is telling you is that if B has this property, then B has to be the whole thing. Okay? Let's see what this is in the case of the natural numbers. In the case of the natural numbers, what is seg? So suppose we are working in the natural numbers with the standard ordering of the natural numbers, and we take a natural number n and we consider the seg of n. What is that going to be? Well, that is exactly 0, 1, n minus 1, which according to our definition of natural numbers, that's the same as n. Okay? So what's that? That's what segment means in that case. In the case of the natural numbers, this is saying, so if A is an ordering of the natural numbers, it's saying that if B is a subset of the natural numbers such that for every n, whenever we have that 0 up to n minus 1 is included in B, then n belongs to B. Then we know that B must be all of the natural numbers, right? This is essentially the induction principle for the natural numbers. You may ask, what happens with the base case? So that sounds pretty much like the inductive case. No, if you have the numbers up to n minus 1, then you have n, then you have n plus 1, and so on. What happens with the inductive case? Well, the empty set is a subset of B, of every set, just because. And so the initial segment of 0 is the empty set, which is a subset of B. Therefore, that property over there, this property, would imply that 0 belongs to B, right? So this property kind of has inside both the base case and the induction and the successor case. Cool, but this is a bit more general, right? Works for every well ordering. That's the idea of this induction principle. How do we prove this? Well, suppose this is not the case. This will prove by contradiction. So suppose B is not all of A. So there must be some element that belongs to A and not B. So A minus B is not empty, right? There is some element that belongs to A and doesn't belong to B. Since A is a well ordering, we can take the least element. Let's call it T0, be the least element of A minus B. The least element that belongs to A and doesn't belong to B. The well ordering property tells us that that always exists for every subset of A. Where is the contradiction? Well, but then every, let's call it little a that belongs to the segment of T0 is not in A minus B. Well, because T0 was the least one, the least element of A minus B. So if you take something that is below, it's not in A minus B, or therefore, or in other words, it's in B, right? If it's not in A minus B, must belong to B, right? So that means that the initial segment below T0 is a subset of B, right? I mean, it's kind of directly, right? We are choosing the least element that is not in B, so everybody below must be in B. And then this, by our assumption on B, we get that T0 must belong to B, that T0 belongs to A minus B. So that's how we get that if you start assuming that B satisfies the inductive set property, then B must be all of A. Cool, so that's the induction principle. We're gonna see examples when we start doing constructions and proofs. So we need to wait a little bit more to see a few examples, but we'll see them soon enough. See you guys later.